Hi, you guys. We're in Genesis chapter 1, and we're going to get through 2 verses and not even get through them. How about that? Let's do this. Okay, Genesis chapter 1. We've been going through the book of Genesis, and I want to start reading in verse 9 because I want to pick up a couple things that I didn't get to last week, and we're going to go up through verse 19. So that's 10 verses, 11 verses. Why don't you all stand? Let's go through and read them together. Starting verse 9, it says, Then God said, Let the waters under the heavens be gathered together into one place, and let the dry land appear, and it was so. And God called the dry land earth, and the gathering together of the waters he called seas, and God saw that it was good. Then God said, Let the earth bring forth grass, the herb that yields seed, and the fruit tree that yields fruit according to its kind, whose seed is in itself on the earth. And it was so. And the earth brought forth grass, the herb that yields seed according to its kind, and the tree that yields fruit, whose seed is in itself according to its kind. And God saw that it was good. So the evening and the morning were the third day. Then God said, Let there be lights in the firmament of the heavens to divide the day from the night, and let them be for signs and seasons and for days and years, and let them be for lights in the firmament of the heavens to give light on the earth. And it was so. Then God made 2 great lights, the greater light to rule the day, the lesser light to rule the night. He made the stars also. God set them in the firmament of the heavens to give light on the earth, and to rule over the day and over the night, and to divide the light from the darkness. And God saw that it was good. So the evening and the morning was the 4th day. Let's stop right there. Let's pray. Thanks, Jesus, for the time that we get to spend together. Thank you, Lord, that when we look out at the creation, it's complex and it's vast, and it's something that only someone with ultimate power could bring into existence. And Lord, as we go through and talk about these things, just want to honor you. Father, it's just cool to think your thoughts after you, to go and look at the creation, see the things that you've done, and have our hearts changed because of the awesome might of the one that we serve and live with and love, Lord. And we just want to give you the study this morning. Pray that you'd bless it, that you'd help me to be clear, and that you bless your people as much as they can be. In Jesus' name, amen. I was kind of joking with that. Again, when we go through and look at the book of Genesis, again, when I was first a believer, I came from the belief that all of the stuff that we see around us has evolved, including, obviously including people, but not just including people, but the whole cosmos itself, the whole universe itself. Last week, we were doing day 3. And so that's dry land and the vegetation. And so what God did was he took the dry land and he caused it to uplift through the waters. So the earth was covered with water first, and then after that the dry land appears. And it looks like it was all in one place. And we talked about this again last week, the whole idea of Pangea. Geologists believe this. And the Bible teaches it in Genesis chapter 1, that he gathered all the land into one place and all the oceans into another place called the land, and obviously the ocean sea. And then you have the creation of the vegetable kingdom, and that's where I wanted to bring in the whole idea of evolution, and specifically chemical evolution, because this is the first time that life appears on the planet. It does not appear in the oceans, according to the Bible. It appears on the land. And one of the things that we talked about was that when you're talking about evolution, generally speaking, and actually I'm saying generally speaking on purpose, they believe that life started in the oceans and came out of the oceans. There are more and more people who are beginning to believe that that's not the case. And so we're gonna be dealing with some of this. We've had attempts to create life, basically. There was the Miller experiment. I talked about this last week. And in that experiment, what they did was they tried to put an atmosphere together that represented the atmosphere on the earth before life ever began, okay? What they were trying to do was come up with what are called amino acids. And so, again, we talked about this last week, but just short overview, amino acids are long chain molecules, which is exactly how it sounds. You have these molecules, they get tied together because of bonds, and they are long chains, right? And you take those molecules, you put them together with other molecules, other amino acids, make longer chains, and you get proteins. And proteins are what you're made of. It's what all life is made of. It's what cells are made of. And so what they were trying to do was come up with amino acids in this little jar right there, okay? And so what they did was they put certain chemicals in right here, heated things up, threw a spark into it, did a condenser. Some of this has to do with getting rid of water, that kind of thing, and they came out with amino acids. And when you're talking about this, one of the things you have to understand is you're trying to come up with an end product. So the end product has certain types of molecules in it. And so what they did was they put certain types of gas with the certain types of molecules in them and took it through this process, and they came out with amino acids, okay? And that is always put in science textbooks as evidence that life just appeared on Earth by chance, accidentally, okay? And again, there's problems with it, and here's a list of some of the problems. These aren't all the problems, but this is a list of some of the problems. Number one, you can't have oxygen, because if you have oxygen involved in this whole process, oxygen tears things down. So when things are rusting, they're oxidizing. When things are burning, they're oxidizing. Oxygen tears basically chemical bonds apart at the molecular level. And so we need oxygen to breathe, but we're equipped to handle oxygen. And so anything that's not equipped to handle oxygen, again, oxygen tears it down. That's why steel rusts, okay? The other thing that you've got a problem with is you can't have oxygen, but then if you don't have oxygen, you have another issue, and that has to do with the ozone layer. The ozone layer comes from oxygen. Ozone layer keeps out UV light, which is some of the bad radiation from the sun. That will break down chemical bonds also. And so it's a catch-22 type of situation. So we talked about that. And then the other issue is water. The one place on this planet that life did not start is in the oceans. You can't have it happening because, again, when you're talking about water, water's kind of like oxygen in the sense that it also breaks down chemical bonds. And so when they did that experiment, they had to get rid of the water. Otherwise, they would not have gotten amino acids. Well, if you're in an ocean, down in a deep heated thermal vent with water all around you, you are not going to get amino acids. It's not going to happen. Life did not start around a thermal vent at the bottom of the ocean. A lot of times when they show movies of evolution and the start of life, what they'll do is they'll have a pond with goo in it on the side of an ocean somewhere near a volcanic, lava vent or something. And what they're doing is they're trying to get it out of the water and at the same time be able to take the water off that comes along through the chemical process. Again, when these chemicals get put together, when these molecules get put together, they throw off molecules of water and it stays in the mixture. If you leave it in the mixture, it all breaks down. So you got to get rid of it. So whenever you see movies like that or videos like that, they always have it around a heat source, and what they're trying to do is get rid of water. Well, when you heat up a protein, you know what that's called? Cooking. That's a barbecue. Okay, that's what it does to proteins. It breaks down the proteins. So again, you can't have that. And then when you're talking about amino acids, you have this whole thing with chirality. There are over 2,000 types of amino acids, and only 20 of them are used in life. So when you do these processes where you're making up amino acids, it's not all of them, it's certain of them. You have to pick out 20 from 2,000 to get life. And then we talked about chirality. This is the idea of molecules that mirror match each other, and life is made up of only left-handed amino acids, these kinds right here. If you take a right-handed amino acid and put it in with a left-handed amino acid, it's immediately poisonous to life. It also breaks up the bonds that go on, and so you can't get the long molecules that you need to have. So 2,000 types of amino acids, only 20 are used in life. They all have to be left-handed. And any of you guys that have taken chemistry, you know that when you do a chemical reaction and you have something like this going on, you're going to get equal parts of both right-handed and left-handed. That's the way that it goes. And so you have to have a way to sift out the right-handed amino acids, otherwise it poisons life. And so again, you have that. And then finally, you have order. There's an order that these things have to be put into. And so it's not just a situation where you take a bunch of amino acids, 20 amino acids, mix them up in a bowl, and they come out with the long chain molecules that will make proteins. They have to be put into a certain order. And if you don't get them in the right order, you don't have a protein. Okay? So all that stuff are huge obstacles to this whole situation. And that's where we got last week. And then on top of it, after you talk about making proteins, then you got to take proteins and you got to make them into something like this. So proteins are just simple molecules, basically, and you're taking them and making them into what people used to call a simple cell, and we know now is nonsense. There is no such thing as a simple cell. The complexity of the cell is ridiculously intense. And so gave you this illustration last time. You can have a Boeing 747. It's made out of 4.5 million non-flying parts. You take a Boeing 747 kit, you take the little parts, you put them into the right places, and in the end, you get something that will fly, like a flying house, basically. You can get something that will fly, but it got to be the right parts, all in the right places, and that's just 4.5 million. When you're talking about a cell, you're talking about billions of parts to get a cell. And so cells are radically more complex than anything that we've ever come up with. So what are the chances of getting all heads, getting this life? And I use an example of flipping a penny. And so here's my penny. It's going to come bouncing in. Boing. Like that? I did that. So this is just talking about chance. Okay, so if I'm going to flip a penny and get heads, what are the chances I get it one time in a row? And the chances of that are 1 in 2 because it's got two sides to it, right? Okay, so it's a 1 in 2 chance. To get 2 heads in a row, it doubles, and now it's 1 in 4. That's the chances. When you go to 3, it's becoming exponential. 3 heads in a row is 1 in 8. If you're going to get 8 heads in a row, it's 1 in 256. Okay, so the chances of getting 100 heads in a row, just with a penny, the chances of doing that are 2 to the 100th or 10 to the 30th power. And that means 1 chance in 1 with 30 zeros behind it to get 100 heads in a row. Okay, and so we're going to talk about there's a reason that I did this. And the reason has to do with getting a protein that has 100 amino acids in it. It's the same chance of getting a long chain protein with 100 amino acids in it. It's the same chance of getting 100 heads in a row, okay? And so here's the situation that we've got. When you're talking about proteins are made up of long chains of amino acids, anywhere from 50 to 30,000 amino acids. So in an amino acid in the first place, you got a molecule that's a long chain, and then you take each one of those amino acid molecules, you put it with another one, you make an even longer chain, and you have to have at least 50 amino acids to get a simple protein up to 30,000 amino acids. And so what we're going to be talking about is the chances of getting a protein with just 100 amino acids. What's the chances of that? 1 in 10 to the 30th. I just showed you that, okay? And so it's got to be 100 amino acids long. It has to come from the 20 amino acids that you can use out of over 20,000. It has to be left-handed amino acids only, and they all have to be in the right order. That's what you're looking at for the simplest form of life. Actually, this is just proteins. Okay, to even approach the simplest form of life, this is what you have to go through, okay? So, if you're going to do left-handed chain of 100 amino acids long, it's 1 in 10 to the 30th, like I said. If you are going to get the right 20 amino acids in order, it becomes 1 in 10 to the 130th power. That's a 1 with 130 zeros behind it, okay? You know what, when I use numbers like this, the numbers are just huge. And so a lot of times, it just becomes kind of like this overwhelming type of situation. Let me give you an illustration. 10 to the 21st power. So that's a 1 with 21 zeros behind it. 1 chance in 10 to the 21st power is like taking silver dollars, we've done this before, and lay them on the face of the earth, and you fill it up 120 feet deep, all over the planet. So 10 to the 21st power is silver dollars, 120 feet deep, all over the earth. You mark one, you throw it in there, you mix it up, you blindfold a guy, he goes through the whole earth, giving every coin an equal chance of being picked, and he picks the right one first time. That's 1 chance in 10 to the 21st. We're talking about 1 chance in 10 to the 130th. 1 chance in 10 to the 50th, according to mathematicians, is an impossibility. It will not happen in the whole history of the universe. And so these are the odds that we're talking about. So when you're talking about, again, a left-handed chain of amino acids, 100 amino acids long, or a protein with 100 amino acids long, 1 in 10 to the 30th, you add the 20 right amino acids in the right order, you get 10 to the 130th. And if you want to talk about a single cell, it's 1 chance in 10 to the 40,000th. Because again, you're talking about multiple proteins, multiple enzymes, all the stuff put into the right place in working order so that it can all go together. This is what Sir Fred Hoyle said. He said, no matter how large the environment one considers, life cannot have had a random beginning. There are about 2,000 enzymes, and the chance of obtaining them all in a random trial is only 1 part in 10 to the 20th to the 2,000th, which equals 10 to the 40,000th. That's a 1 with 40,000 zeros behind it. There's only 10 to the 80th electrons in the universe, much less 10 to the 40,000th. It's an outrageously small probability that could not be faced even if the whole universe consisted of organic soup. This guy is not a Christian. And so you take the whole universe, fill it up with organic soup, not just a little pool on the side of an ocean someplace. Take the universe, fill it up, and try to get the 2,000 enzymes we need for life, and you're not going to do it. Not in the history of the universe. It cannot happen. Okay? So there's another guy, Francis Crick. This guy, you may be familiar with him. He was the guy, one of the guys who discovered the double helix nature of DNA. You know, where it's kind of a ladder all twisted around, DNA. So he discovered that, got a Nobel Prize for it. And he said, if a particular amino acid sequence was selected by chance, how rare an event would this be? The great majority of sequences can never have been synthesized at all at any time. And so that's his position. He actually, because of this situation, because he knew that the probability of life evolving from chemicals on this planet were so low, he came up with the idea of what's called directed panspermia. Panspermia means taking seed and sending it out everywhere. And so he had the idea that aliens took DNA and shot it off in rockets, and some of it landed on our planet, and that's where the first life came from. First DNA molecules specifically came from the aliens who shot them off in their little rockets. Okay, you know why aliens can do that? Because aliens can do anything. You know why aliens can do anything? Because we don't know any. And so this guy's not a stupid guy. And so he had to come up with the aliens did it, E.T. did it. Here's another guy, Robert Gange, said this: the likelihood of life having occurred through a chemical accident is for all intents and purposes 0. This is an abstract from Crick, Francis Crick again, same guy, where he's talking about directed panspermia. This is actually from a paper that he did. He says this: it now seems unlikely that extraterrestrial living organisms could have reached the Earth either as spores driven by the radiation pressure from another star or as living organisms embedded in a meteorite. What he's talking about is there are some people who believe that meteorites with DNA on them hit the Earth, or that spores were going out through space. As an alternative to these 19th century mechanisms, we've considered directed panspermia, the theory that organisms were deliberately transmitted to the Earth by intelligent beings on another planet. We conclude that it is possible that life reached the Earth in this way, but that the scientific evidence is inadequate at the present time to say anything about the probability. In other words, we don't know that it happened, but maybe that happened. Michael Denton said this: British astronomer Fred Hoyle, he's another one who came up with this, and Chandra Wickramasinghe have also recently raised the possibility of panspermia. Nothing illustrates more clearly just how intractable a problem, that means how hard a problem, the origin of life has become than the fact that world authorities can seriously toy with the idea of panspermia. Fred Hoyle said this about the genesis of life. He says, the chance that higher life forms might have emerged through evolutionary processes is comparable with the chance that a tornado sweeping through a junkyard might assemble a Boeing 747 from the material therein. And again, it's just an impossibility. And so here's the deal, you guys. When I became a Christian, I didn't have to check my brain in at the door. I don't have to believe nonsense. And one of the things that I found when I did become a Christian was I found people coming up with a different viewpoint than what I was taught in school. And what I was taught in school, I found out almost everything that had to do with evolution or with astrophysics, almost everything that I dealt with, I only had half the information. I only got the positive on those issues. I never got the negative on those issues. And so I had no way of knowing whether these things were true. Basically, what I was doing was spouting off stuff that I got from textbooks, and I hadn't checked it out. And so, again, this is one of those things that I didn't know. When I first learned this, I learned this from I went to a seminar from a guy who had 3 earned PhDs. No, I think he had 4. Was it 4, Bobby? Yeah, I think it was 4 earned PhDs. And he was a chemist. And so he just goes through and he starts describing the chemistry in more detail than what I did. But he started describing the chemistry. And I keep all my books. So I have my college chemistry book. And I went home, picked it up, opened it up, looked at the whole issue with the bonding and amino acids. It was in there. It's all written in there, you guys. And I just hadn't put those things together. And it's absolutely true. And so you have that. And, we still have good reason to believe this. For by him all things were created that are in heaven and that are on earth, visible and invisible, whether thrones or dominions or principalities or powers. All things were created through him and for him, and he is before all things, and in him all things consist. The reason, again, that I'm putting this at this part of the whole thing is this is when life starts. You can't get past the beginning of life, much less talk about going from one life form to another life form and getting into the higher echelons of life. You have huge issues when you start talking about the complexity of animal systems. They're huge. They're insurmountable. And it didn't happen from mutations and that kind of thing. So when you're talking about evolution, you're not just talking about, have you guys heard about the missing link? Like the missing link? Have you heard of this? Yeah, it's not the missing link. It's millions of missing links. There should be more missing links than there are fully formed animals on this planet. There should be more in-betweens than there are fully formed animals. And so what they did, I'll deal with that later. Basically, you go from rat to bat, There's all kinds of little transitions between rat to bat, and we don't see any of the transitions. We see fully formed rats, we see fully formed bats, we see nothing in between. And that's with every animal on this planet on every level, whether you're talking about from single-celled all the way up to multi-celled, all the way up to humans. You have the same exact issues, and there is no evidence of transitional forms. None. No evidence of transitional forms, and there should be nothing but transitional forms. So you know how they handled it? It's called the hopeful monster theory, punctuated equilibrium. It's the idea of the X-Men. So with you guys know the X-Men, right? And so with the X-Men, what happened is over a short period of time, we've had some mutations that have taken place, and all of a sudden I can fly. All of a sudden I can have laser beams coming out of my eyes. And then all of a sudden I can make the weather change. All of a sudden. That's called punctuated equilibrium. Daddy and mommy have a kid, and they come out with superpowers. It's that idea. And so a couple of lizards have a kid, and it comes out a chicken. And I'm being simplistic with that. You know, what they're talking about is over a very short period of time. So short a period of time that you can't see it in the fossil record, you get all these radical changes. So what they're admitting is there's no evidence in the fossil record, but on the other hand, we don't see evolution because evolution takes too long. So when we look at living animals, we don't see any evidence of evolution. But when we look at the fossil record, we don't see any evidence of evolution. When you're looking at living animals, they say it takes too long. When you're looking at the fossil record, they say it happened in such a short time that there's no record of it. That explains everything, doesn't it? It's not falsifiable, is the point I'm making. Okay, so then you get to the sun and the moon and the stars. Okay, and this is one of those places where I had, again, some real problems, because in verse 14, God says, let there be lights in the firmament of the heavens, and we find out that two great lights are made in verse 16. That's the sun, and then the moon, and then he made the stars also in verse 16. You know how vast this universe is? You know, what we're talking about is deep time. So when you're talking about from the evolutionary point of view, you are talking about deep time, 13.7.87, I think it is now, almost 13.8 billion years ago is when this stuff all started. And so when you're talking about light that's reaching from that distance, you're talking about more than 13 because the universe stretches at the same time that the light's coming towards you. And I'm not going to get into that. But anyway, you're talking about, you look out 13.8 billion light years, and that light has supposedly been traveling at you for that long a period of time, and you got a time problem with the Bible here, because if God creates all the stars on day 4, we're still not seeing them all, because if day 4 is about 6,000 years ago, then we'd only be able to see about 6,000 light years out if it's all working in the way that they say that it works, right? And so now I got a problem, because the universe is vast. It's huge. And light, we can see light from as far as we can see. I'll show you some pictures in a minute. And so you have that whole thing. One of the issues that you need to keep in mind when we're talking about creation in the first place is that whenever you create anything, there is an apparent age to the thing that's made, okay? And so the way I always illustrate this is Adam. So on the day that Adam's created, say he's created at 6 in the morning, and you go and visit him at 12 noon, how old is Adam? Yeah, he's 6 hours old, right? It's been, it's his first day, right? So he's 6 hours old, and how old does he look? And so obviously, Adam has to be old enough to have kids. He has to be old enough to take care of himself, take care of his wife, take care of his kids, that kind of thing. So how old is Adam on the day that he's created? And so, I don't know, optimum, maybe somewhere around 20, about my age. Yeah. So say he's about 20, he has an apparent age of 20 years old. And so you walk up on the guy and look at him and go, wow, the guy's a good-looking 20-year-old, because he's perfect, right? good-looking 20-year-old, and then you say, hey, how old are you? 6 hours. What are you talking about? And you're going to have a conversation with him, and he's going to go, really? I knew nothing, until 6 hours ago. Got up, shook off a little dust that was left over, and God said, hi there, Adam, here you are. And so you have that. You have that in the New Testament too. When Jesus fed the 5,000, right? So what he's doing is taking a kid's lunch, he's multiplying it, and there's an apparent age to that. So you come up and you give me a piece of fried fish, it's cooked fish, and you hand it to me, I'm not gonna believe that you just created that. There's an apparent age to it. And so you start going backwards. The fish has to get to me, so you walk to me. That's how old it is at the very least. You walk to me from your home, right? You cooked it, so call it 15 minutes. Well, it's probably burning it, but 15 minutes in the frying pan. And before that, it had to be a fish, and it had to be a fish big enough to catch. So I don't know, 6 months, a year old. It's got to be, and before that, it's an egg and comes from a mommy and daddy fish, and all that. There's an apparent age to that, right? Well, you have that with anything. So if there's a creation, then it looks like it's older than it is in the first place. And so that's one of those things that you can look at and you could say, okay, there's an apparent age to this. So if I made this right here, this table, the top's made of wood. Well, the wood has to come from a tree. The tree has to be, a seedling. It comes from a seed. It grows up. It gets cut down. It gets processed. And then you get the steel down here and all this stuff. There's an apparent age to this. And if I just went poof, and there it is, it looks older than it is. Follow that? Okay. So that's one of those things that I used with this, but there's still problems with that. Because if I come up to Adam and he looks like he's 20 years old, and he says, no, I'm only 6 years old. And I go, oh, really? And then I'm having a conversation with him, and pretty soon he pulls out his phone, and he's going through, and he's showing me pictures of his childhood. Well, what are you talking about? You just told me you're 6 hours old. That's contradictory, right? And so when you're looking at the universe, when we look at the universe, things explode. And so there are things that are light years away. A light year is a distance. It's not a time. It's the distance that light travels in a year. It's about 6 trillion miles. So light travels about that distance in a year, and so you got things that are light years out there that blow up. So for example, the sunlight that you see from the sun, it's 9 minutes old. The sun could go out, and for 9 minutes, you don't know it. It could just go blank. You don't know it for 9 minutes. The light that comes from the moon was full this morning, 1.5 seconds old. So when I'm looking at the light from the moon, it's light that's come from the sun, bounced off, and it takes a minute or a second and a half to get to me. That's why there's a delay in the communications with the Apollo astronauts on the moon. And so again, you have that. And so there are things that are way out there that have exploded. There's like a history that's there. And so you can't just say it's an apparent age to the universe, because otherwise what you got is Adam with pictures of his childhood and his parents in his cell phone. And you can't have that. He should have none of that. And so there's a problem there. Okay, so one of the things I want to talk to you about right now is the evolutionary idea of where the universe came from. So I want to talk to you about the Big Bang. And so there's a couple things I got to do with you before I can even get into this. And so it has to do with redshift. We've talked about this before, but now I have pictures. Okay? So this is what's called redshift. And when you're looking at redshift, let me go backwards here. When you're looking at redshift, you have a light spectrum, and this right here is just a rainbow. When the sun refracts through raindrops, you get the spectrum of the white light that comes from the sun, and it goes all the way from ultraviolet to infrared, okay? And so this is all light. Ultraviolet light is radiation. Infrared light is heat, okay? And so when we have all these things that we divide stuff up into, but it all is light, right? And so it just depends on how fast the light is going, basically. It's all made out of particles. And so what the redshift is, it has to do with something that gives off light and it's moving. So this is a star and it's moving towards this dude. And when that happens, the wavelengths, light is a wave, has a wave properties, they get squished. They get pushed together because he and the star are coming together. So these get squished. And when light is going away from you, when a star is moving that direction, they get lengthened out. That's called redshift. Okay, here's another picture for you. So here's that spectrum again. And so when you have a galaxy that's moving toward the Earth, it's shifted to the blue, and the light gets all squished up like this, the wavelengths of the light. And so that's called a blue shift. And when it's moving away from you, it gets all spread out, and so that's called a red shift. Okay, this is how that works practically speaking. I'm on the Earth, I'm examining these galaxies. And in these galaxies, they have light from certain stars, they have spectra from certain stars. You know that stars are made mostly of hydrogen, for example. And when you look at a spectra of stars, galaxies, supernova, those kinds of things, they have these bands on them that identify what they're made of, okay? And so when they are looking at, for example, this galaxy right here, it may have this band that's right here that let's say it's the hydrogen band. It may have this band that's right here and it sits right there, and so we don't know a lot about that except for that band's right there. But then we look out at a galaxy and we see exactly the same makeup of that chemical with these bands, but now it's shifted this direction. And that's called a redshift. And the farther out you go, the farther these bands go this direction. That's what the redshift is all about. And it's an indication that these are quickly moving away from us. And that's where you got the whole idea of the Big Bang. When they first started looking at this stuff, they realized when I look out and I look at the distant galaxies, they're shifted towards the red, so that must mean that they're moving quickly away from us, and the further in we come, the less you have that redshift, right? And so everything's moving away from us. Well, if everything's moving away from us, then if you go back in time, then everything was in one place. And that's where you get the whole idea of the Big Bang. That's where it came from. Everything was in a particle, type of situation, and it blew up and it moved out, okay? You guys get that? Okay, so that's the whole idea of the red shift. When you're looking at the issues that go along with the Big Bang, there are some problems with this. And again, this is actually, I want to go back. This is kind of the idea behind the Big Bang. Everything you have in the universe was in one small spot. It was called a singularity, just a name. One small spot, and then what happened was there was an explosion, but it's an explosion not just of matter into space, it's an expansion of space and time. And so, bam, there's the explosion, and space and time move out, and then you get galaxies, and they're moving out with the same, in the same situation. This is what I'm telling you. When you're talking about the Big Bang, it's not a situation where you had empty space, all the matter in the universe in one spot, and then boom, it explodes and goes out into empty space. When you're talking about the Big Bang model, what you're talking about is all of space, all of time, everything that, all of energy and mass is all in one place. Literally, the universe is expanding, okay? It's not stuff in the universe. The universe is expanding into another dimension, basically. Sorry. In any case, that's the Big Bang. And so here's kind of how this looks. So you start off with the singularity, and then this is the hot part of the Big Bang. The universe is expanding as time goes on, and it's got all these galaxies that are embedded in it, and it keeps going on like that. It's kind of like a balloon. Here's my prop. This is the only prop I think that I've ever used, okay? And so my secretary, Christy, made this for me, and it's a balloon with all kinds of little marks on it that are like galaxies, okay? So this is how the Big Bang is explained. You take all these little marks on it, they're pretty close together, and you begin blowing it up. And if I get ink on it, the ink is leaking, right? It's not dried. So if I get it on my lips, you have to tell me so I don't look stupid up here the whole rest of the, anyway. So as you blow this up, what happens is everything starts getting farther away from everything, right? And so you can pick like this little galaxy right here. It doesn't matter where you pick it on here. As the balloon expands, what's going to happen is it's going to be getting more and more distant from everything. So watch. So it gets a little more distant, a little more distant, and it keeps doing that. And that's the idea. This is what's called the Copernican theory of the Big Bang. It's the idea that there is no point in space that's special. Everything is expanding away from everything. So if I'm sitting here, let's go backwards with this. If I'm sitting here and we start going backwards, it looks like everything's getting closer to that. And so from your point of view, it would look like you're in the center. But it would be the same thing on this side. Okay? So it would keep go back like that, and then you get back to the singularity. Okay, so that's the idea of the Big Bang without a bounded universe. That's with an unbounded universe. And it doesn't quite work. This is like, it's actually a two-dimensional description of three dimensions. You have to, the inside of that would be hyperspace or whatever. Anyway, that's what's being pictured here. And you have the same thing. This is that balloon illustration as it goes up. I just wanted to use my little balloon. So here's the Big Bang over time, okay? So this again it's just a graph, it's just an illustration, but over here you have this point, a small point, then there's a huge inflation. And if you look at this line right here, it's spreading out, but not very quickly, over 13.7 billion years, okay? It's not spreading out very quickly, it's pretty flat. And so you're going from a small dot to something the size of the universe. That's called cosmic inflation. And then from that point on, you start going off in time. Well, there's some things that you can assume from this. One of the things is that you can look back in time. So I'm sitting out here on the edge of this whole thing, and I want to look at something a long ways away. Well, if light takes 1 light year for every year to get to me, if I'm looking 13.7 billion years back, then I'm going to be looking back at things that look like this. They're going to look young, okay? And so I'm looking from here, I'm looking at really distant objects, and they should look like this. Young objects that don't have the same structure that I have in things that are around me. Is that what we find? And some of you are shaking your head, no. That is not what we find. This is an example of this. This is the Hubble Ultra Deep Field. It was taken in 2014. The galaxies, what they did was they basically picked a blank spot in space where you couldn't see anything with normal telescopes. They turned the Hubble towards that, and they started taking pictures, taking long exposures. This is what they got. All of these galaxies, these are all galaxies. All of these galaxies are between 5 and 10 billion light years away. And so if that whole light year per year thing works, then they should be 5 to 10 billion years in the past. But when you look at these things, it doesn't matter where you're looking. What you're seeing is objects that are just like the objects that we see around us. And so you can zoom in on these things. That's a spiral galaxy right there. And you have globular galaxies. This is probably another spiral galaxy right here. The point that I'm making here is these structures are back in deep time. If, like I said, that whole thing is the way that they say it is, they're back in deep time and they look exactly like everything around us. And that's not what should be happening. And so this is a big issue with the Big Bang, okay? So as far as we can see, it all looks the same, okay? Here's another thing. When I have talked with guys about what the Bible has to say, actually, usually people are attacking me, and when I'm defending the position, one of the things that people like to do is they like to say, well, you got a light speed problem, Steve, Because if you got, the Bible's talking about 6,000 years of history, and we know that we've got at least 13.6 something billion years of history, because that's how far out we can see, assuming the speed of light has never changed, right? And so that's what we can see. So here I am on the earth right here, and I'm looking out about 13.8 billion years, and I'm seeing what's called the cosmic microwave background radiation. We'll talk about that a little bit more in a minute. But you look out and you see these distant stars, this distant radiation, and that's 13.8 billion years. Well, if I turn around and look this way, I'm seeing the same thing. And so now you add those two numbers, 13.8 plus another 13.8, you get 27.6 billion years, billion light years, but year to a light year. Let's do that. 27.6 billion light years. Well, the universe is only about 13.8 billion years old, 13.7 some odd. Here's a problem that we've got with this. This right here is 27 billion light years from this right here. You only have 13.8 billion years to work with. So this right here cannot see this right here. You guys follow that? The only thing that can be seen, I'm right here, I can see this far because that's all the time that I've got. There's not enough time for a guy over here to see this over here. All he can see is me. You guys get that? Okay, that's called the horizon problem. And basically what's happened is when we look out at the microwave background radiation, it's within hundreds of thousands of a degree smooth. It's like almost exactly the same temperature everywhere we look. Remember what temperature is? It's the infrared end of the spectrum, right? So what we're talking about is light. So light from here has the same, or this radiation from here has the same temperature as radiation over here, as radiation over here, as radiation over here, as radiation over here. And you'll see these pictures of the cosmic background radiation, and it'll be all variable, but you're talking about thousands of a degree in difference. It's the same temperature everywhere we look. And the problem with that is you can't have that. You have an explosion, and these things are out of communication with each other. You should be seeing different temperatures all around here unless they had communicated with each other. And there's not enough time for that. And so they've got a light speed problem. So I got a light speed problem. Big bangers have a light speed problem. So it doesn't matter who you're talking about. And so again, not enough time for light to have traveled across the visible universe. Here's another problem that you have with a Big Bang, and it's called the flatness problem. It's a little bit more complex, but this is pretty cool. These are graph images. I got this off of Wikipedia. Graph images of the density of the universe and how this would look. This is a flat universe. This is a universe that's expanding and is never going to come back together, expanding quickly and is never going to come back together. This is a graph of a universe that expands for a period of time, then falls back in on itself because it's got too much density to it. The gravity squishes it, okay? And so here's what's interesting about this whole thing, is this graph. When you're talking about, this is omega. Omega is just talking about density, so I'm just gonna fill it with that. If the density of the universe does not equal 1, then the value changes with cosmic time. If the density of the universe is more than 1, then it grows larger and larger. If the density of the universe is smaller than 1, it's just a random number that they've given, then it grows smaller and smaller. And this is the idea behind it. We're sitting out here, okay? This is time, cosmic time. This is the beginning right here, so that's the Big Bang. And we start going off in cosmic time. And what we found is we're out here, we're here someplace, and this line, the density of the universe, how quickly things are moving apart, is sitting down here somewhere. So let's see, how am I going to explain this to you? If this was just slightly above 1 at the beginning, then you have this curve that takes place, and you have a universe that's going to be so heavy that it falls in on itself, and you don't have time to make galaxies and stuff. If the universe is slightly below 1, then you're going to have a universe that is so spread out that it's just going to go flying apart, and again, you don't have time to get stars and galaxies and that kind of stuff. What they have found is that the universe is almost flat. This line is almost flat, and so the picture is this right here. We have a universe that looks somewhat like this. And again, it's just a graph. So if the density had been much above 1, it would have recollapsed very early before making galaxies. If the density had been much below 1, it would have expanded so rapidly that structures would not have formed. That requires a lot of fine-tuning, and here's why. When you're looking at this, these numbers go up exponentially as time goes on. And so if you're sitting right here and we're seeing something that, where there's a line that's almost right here, by the time that you get back in time, it has to be so close to 1, just barely above 1, that radical curve there doesn't make much of a difference. And the point is that the universe is fine-tuned. Let me go to this next one. If the universe is approximately flat right now, it had to be very, very flat at early times. Just think of that line. If the density is about 1 right now, that means the density at t equals 1 second after the Big Bang, differed from 1 by less than 1 part in 10 to the negative 16th. That number is, you take a decimal point, put 16 zeros in it, and write a 1, and that's how close to 1 that can be for it to be what we see right now. At the Planck's time, which is an important thing that you don't care about, at the Planck's time, the density differed from 1 by less than 1 part in 10 to the 60th. So again, take a decimal point, put 60 zeros, mark down a 1. That's how close it had to be at 1 at the very beginning. This is the point. Of all the universes that we have, all the options that we have, there are many more, vastly more options for a universe that would be above 1 or below 1, and we are so close to 1 that at the time that we're at, even with that curve, at the time that we're at, we still have a universe that's almost flat with a very slight expansion that's taking place, and it keeps our universe stable. The whole point that I'm making here is this is designed. This is designed. And so, again, if omega had been much below 1, it would have expanded so rapidly that structures would not have formed, and this is what I put in, God signed the universe for you. It's like putting his name on it. And so that's a cool thing. Here's another thing. Let me go back to this. Okay, so when you look at this graph, what we're seeing here is we're clear out here, and we're seeing a density that looks like this right here. Okay, well, this is time, right? And so what I'm telling you is if we're seeing a density that looks like this right here, when we should be seeing something that's more like this or more like this, if it's all just random, then what we have is either it's radically fine-tuned and designed, or it's not as old as we think it is. Because when you go back in time, this number gets closer and closer to 1. Follow that? So either way, it's something that contradicts the Big Bang. There. Aren't you blessed by that? Yeah. Okay, so this is what they came up with to fix it. They know that they've got a problem. They figured this out it was probably in the late 50s, early 60s. They've known that they've had this problem the whole time. It wasn't until the 80s that a guy came up with a solution to the problem. And the solution is cosmic inflation. And I just pulled this definition off the internet. In physical cosmology, cosmic inflation, cosmological inflation, or just inflation, is a theory of exponential expansion of the universe and of space in the early universe. The inflationary epoch lasted 10 to the negative 36 seconds after the Big Bang. Singularity to sometime between 10 to the negative 33rd and 10 to the negative 32nd seconds after the singularity. Fraction of an inch, of a second. Very small period of time. And in that very small period of time, the universe inflated from a point all the way to something that's the size of the universe, okay? And so following the inflationary period, the universe continued to expand, but the expansion was no longer accelerating. Okay, so here's that previous picture that I gave you of the whole Big Bang. That's the particle, that's the singularity at the very beginning. Then you have cosmic inflation, that's this next part, and then you have these long ages where there's slight expansion. But small point, boom, cosmic inflation. This is universe-sized. Cosmic inflation, and then expansion up until modern times. And so this is the inflationary period, okay? This is actually a picture of that graph that I was telling you about, or that image that I was telling you about with the microwave background radiation. Okay, so from nothing to huge. Okay, so what started it? And they don't know. Then it had to stop. So what stopped it? And they don't know. What kept it from being something that was all over the page? Like in this part, it expands radically quickly. This part, it's less quick, you know, and so on. What kept those things from happening? And they don't know. What evidence do we have for this? None. We have no evidence. This is an ad hoc explanation to save the Big Bang. This is from John Kramer. He said this: the problem with all of this is that the inflation scenario seems rather contrived and raises many unresolved questions. Why is the universe created with the inflation field displaced from equilibrium? In other words, it has an equal power everywhere. Why is the displacement the same everywhere? What are the initial conditions that produce inflation? How can the inflationary phase be made to last long enough to produce our universe? Thus, the inflation scenario, which was invented to eliminate the contrived initial conditions of the Big Bang model, apparently needs contrived initial conditions of its own. And the point is, what they were doing was trying to save the Big Bang. Because those problems that I gave you, there's others. Magnetic monopoles. You guys watch The Big Bang Theory? Our whole universe was in a hot, dense state. Then 13 million years ago, expansion started. Wait. Oh. Anyway, there's an episode where Sheldon goes to the North Pole and he's looking for magnetic monopoles. And the reason he's doing that is because he's an astrophysicist, and he's trying to find evidence for the Big Bang. It's another huge problem that you don't care about. But anyway, what I'm telling you is there's problems with the Big Bang. As a general, Haltenharp, I like this guy. As a general scientific principle, it's undesirable to depend crucially on what is unobservable to explain what is observable, as happens frequently in Big Bang cosmology. He went on to say, when Big Bang proponents make assertions such as the evidence taken together hangs together beautifully, they overlook observational facts that have been piling up for 25 years and that have now become overwhelming. Of course, if one ignores contradictory observations, one can claim to have an elegant or robust theory, but it isn't science. And again, that's what you have with the Big Bang. I've been actually, you know what? When you're talking about scientific theories and scientific positions, they're called paradigms. And usually, a scientific paradigm hangs around until they have something better to replace it with. And so what you will see is scientists who hold on to an explanation, for example, in this situation, for the universe. They hold on to the theory, they keep propping it up with nice stories, like the inflationary period. They keep doing this until they can find something that better fits the facts, and then they go, oh, never mind, none of that was true. This happens over and over in science, except with some people. And so, okay, so what's that got to do with me, Steve? This is what it's got to do with you. I want you to know that when you are talking to people who know this stuff, a lot of times what you're getting is you're getting half of the story. They're not telling you the problems with it. And you need to know that there are problems with it. We have a whole culture nowadays that tries to make science and scientists their religion. You know, I believe in science, Esteban said. And so, you have this situation where people are standing on this kind of thing, and some of them are Christians. They're holding up the Big Bang as the way that God created the universe, and there are huge problems with the Big Bang, and it's on its way out. And we just haven't experienced that whole thing yet. I don't expect you to remember all this stuff, except for remember horizon problem, remember flatness problem, remember old structures in a young universe. Those are the things I just told you. And if somebody comes up to you and goes, well, the Big Bang, blah, 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 blah. Well, what about the flatness problem, buddy? What about that? Well, what are you talking about? Oh, you better go check it out. Because you don't know anything about the flatness problem. I know some stuff about the flatness problem. Well, tell me. No. You go look it up yourself. What about light speed? Blah, 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 Well, you need to go look that up yourself because you got a horizon issue, Bucky. So there's the horizon problem. Well, what's the horizon problem? I'm not going to tell you. You should have known your stuff. What are you doing coming here talking to me about the Big Bang? You don't even know about the horizon problem. What's your deal? I've actually done that with people. In any case, again, all these things that are held up as certainties are not certain on any kind of level. And the things that they come up with to try to prop up those certainties are things that have no evidence for them. You can't find it. And so, again, you have that. There's a reason that God made the universe vast. As the heavens are high above the earth, so great is God's compassion for those who fear him. Heaven's vast. The universe is vast. We can't see it all yet. We can't see everything that we could see yet. It's huge. God says in the book of Jeremiah, if you can count the stars, I'll forget my covenant with Israel. And the amount of stars is vast. It's overwhelmingly vast. And every time God uses the heavens as an example, it's something that he uses to show his compassion, how compassionate he is, how trustworthy he is, how powerful he is. It says he holds the heavens in the span of his hand. That's from here to here. Holds the heavens in the span of his hand. God's powerful. He's compassionate. He's absolutely trustworthy. When he gives his word, he keeps it. And those are just a few of the verses. And so this stuff's cool. And again, when I found this stuff out, it makes me feel a whole lot better. Okay. Next week, we're done right now. Next week, I'm going to go in and talk a little bit about some theories about how to deal with this whole light speed issue. One of the ladies, when we first started the Genesis studies, I was talking about 13 billion years and that whole thing. And she said, Steve, I thought that the Bible indicates that the earth is way younger than that. And I said, oh yeah, it does. And so there are ways to reconcile these things. And so we're gonna be talking about some cool stuff next week. So don't miss next week. Let's pray, because I don't want to repeat it. Let's pray and we'll get you out of here. Thank you, God, again for your word. Thank you, Lord, so much for the love that you have for us. Thank you for the fact that we serve and honor and live for a God who is overwhelmingly powerful. And Lord, as we look at your creation, you've said about it that the heavens declare the glory of God and the firmament shows his handiwork. Day unto day, it utters its speech. There's not a language where people can't understand this. And God, it's just a cool thing that you've done. Lord, we just pray that as we go our way, that our lives would be honorable to you, that you'd open up opportunities for us to share your love with the people who are around us. And God, I just really like it that I don't have to check my brain in at the door. You have answers. And so just give you the rest of the day. Pray that you bless it all in Jesus' name. Amen.